Hello students, in this video we are going to discuss 9.5, 9.6 and 9.7 from the ray optics and optical instruments. Coming to 9.5, a small bulb is placed at the bottom of a tank containing water to a depth of 80 centimeter. What is the area of the surface of water through which light from the bulb can emerge out? The refractive index of water is 1.33. Consider the bulb to be a point source. This model problem is asked in this year 2025 in the CBSE board examination. And this related concept I have explained with the name of Snell's window in the ray optics and optical instruments. In the given box, in the description box, I will give you the link. Please go through the concept. Now the situation is like this. This is the tank. The water is up to here and there is a bulb here acting as like point source. From here the rays are coming out, from which they will undergo along the interface. We need to find out this area. Assume that this is side H and it is radius R. We need to find out the area of the surface of the water through which the light from the bulb can emerge out. This area we need to. According to the given data, the refractive index of the water is given as 1.33. That is also nothing but 4/3. And this H value, that is height of the water or depth of the water, is 80 centimeter. That is also nothing but 0.8 meter. Now we need to find out the area. Actually, in the concept I have derived the expression for the radius R is equal to H by mu square minus 1. After derivation, we got this expression. We'll use the same. From this, we can write A is equal to pi R square. That is also nothing but pi H square divided by mu square minus 1. Just to substitute the values and simplify. Pi is nothing but 3.14. H is 0.8 whole square divided by mu square is nothing but 4/3 whole square minus 1. That is equal to 3.14 into 0.64 divided by, we can write here 7. It comes to numerator 9. So 4/3 whole square minus 1 will becomes 7/9. So after simplification, this value will be nearly 2.58 meter square. So this is the area and solution for this problem. Coming to 9.6. A prism is made of glass of unknown refractive index. A parallel beam of light is incident on a face of the prism. The angle of minimum deviation is measured to be 40 degrees. What is the refractive index of the material of the prism? The refracting angle of the prism is 60 degrees. If the prism is placed in water of refractive index 1.33, Predict the new angle of minimum deviation of parallel beam of light. Here are two subcases. One thing is we need to find out the refractive index of the prism whenever it is placed in air. So whenever it is placed in water, we need to find out the minimum angle of deviation. According to the given data, angle of the prism is 60 degrees and the angle of deviation is equal to 40 degrees. It is in air when the prism is placed. And the refractive index of the liquid is equal to, there is nothing but water is nothing but 1.33, or there is also nothing but 4/3. We need to find out refractive index of the prism. There is nothing but a glass. We need to find out in air pure. So we can use the formula refractive index of the glass in air is equal to sine of A plus delta m by 2 divided by sine A by 2. That is equal to sine of 60 plus 40 divided by 2 divided by sine 60 by 2. That is also nothing but sine 50 degrees. It is sine 30. We are aware of sine 30, but we don't know sine 50. We can take the help of natural sine. From that we can get sine 50 is 0.7660 divided by it is 0.5. So after simplification we will get 1.532. So that is the refractive index of the prism. Refractive index of the glass prism. Now when this prism is placed in water, then the formula refractive index of the prism or glass with respect to water is equal to sine of A plus angle of prism will be remain same, but angle of deviation will differ. Delta m dash I am writing by 2. The delta m dash only we are going to find out, divided by sine A by 2. Now here the left hand side part, refractive index of the glass with respect to water, can be written as refractive index of the glass with respect to air divided by refractive index of water with respect to air. That is equal to sine of 60 plus delta m dash divided by 2 divided by sine 30. That is sine 60 by 2. We are aware of refractive index of the glass with respect to air, refractive index of the water, nothing but liquid here, with respect to air. So now by substituting these values, 1.532 we got refractive index of the prism, divided by, for water 1.33, that is equal to sine of 60 plus delta m dash divided by 2 divided by sine 30. So from this we can write sine of 60 plus delta m dash divided by 2 is equal to 1.532 divided by 1.33 into sin 30. Sin 30 is nothing but 0.5. So after simplification, we will get 0.5759. This is sine of 60 plus delta m by 2. So now 30 degrees plus delta m dash by 2. Now this 2 is denominator only for delta m dash. That is equal to sine inverse of 0.5759. This value will be 35 degrees 10 minutes. This one we can get it with the help of natural sine. That is 30 plus delta m dash by 2. So after simplification, delta m dash is equal to